Well, once again, we have a video for Off-Campus Learning Day. We're going to pick up where we left off on part 4 of 4 random variables. Part 4 of 4. We're doing the cereal problem where X represented the random amount of cereal that ends up in a small bowl. And Y is the random amount of cereal. It's not yogurt. It's a large bowl of cereal this time, but the underlying mathematical idea is the same. Now in part D, the question is, what are the mean and standard deviation of the total amount? So not the difference of the amount, but this time the total amount. So the model that we're going to use is small bowl plus large bowl. So I think it'd be reasonable to calculate the mean as the expected value of X plus Y. That's expected value of X plus expected value of Y. And the small bowl was 1.5 ounces, the large bowl was 2.5, so 4 ounces is the mean amount. If we combine a large bowl and a small bowl of cereal, we'll get 4 ounces on average. What's the standard deviation of that going to be? Well, I think it's going to be the square root of the sum of the variances. So for the small bowl, the standard deviation was 3, so the variance is 0.3 squared, 0.4 squared, so it was that 3, 4, 5 triangle thing. Square root of 0.25 is 0.09 plus 0.16. So that square root is going to be 0.5 ounces. So standard deviation, same as the difference. Notice that variances add whether you add or subtract. The variance when we subtracted, the variance is added when we subtract, you get 0.5 ounces. So that's the same over here. No surprise that the standard deviation is the same when we add or subtract bowls of cereal. Part E, if the total of the 2 bowls, so by the total they're referring to X plus Y, follows a normal model, what's the probability that you poured out more than 4.5 ounces? We're expecting 4. In the 2 bowls together, what's the probability that this distribution for X plus Y, which is a normal model with a mean of 4 and a standard deviation of 0.5, what's the probability that we pour out a total of more than 4.5 ounces? At this point, I hope that you would press pause on the video, try to work this one out on your own, and then come back to see how you did. We're back, so let's work out the mechanics here. I need a z-score for 4.5. Using x minus mu over sigma, where that's a generic x. It's not referring to the same x as this, but this is just a generic value of x plus y, of the sum of x and y. So watch out for the potential for confusion there. We're taking 4.5 minus 4 divided by the standard deviation was 0.5. So that should be a z-score of 1. And so we go to the calculator and do normal CDF from 1 to 999. So normal CDF of 1 comma 999. That should give us 0.1586. Arrow that in. Remember, there's 4 numbers, a center, a cutoff, a z-value for the cutoff, and this. So we are going to, total follows a normal model. We'll use a normal model with a mean of 4, standard deviation of 0.5. And probability that comes out to be more than 4.5 ounces is approximately 0.1586. Part F, the amount of cereal the manufacturer puts in the boxes is a random variable. So now we have X is a small bowl, Y is a large bowl, and the amount that the manufacturer puts in, we'll call that Z. We're going to let Z represent the amount of cereal in the box. So the expected value of Z is 16.3. Maybe they advertise it's a 16-ounce box, but they err to the upside there. So E of Z is 16.3 OZ ounces. And the standard deviation of Z is given as 0.2 ounces. So I would like you to think about what would be the model for the amount of cereal that's left in the box after you pour out a large bowl and then pour out a small bowl. How can I use X, Y, and Z to create that model? I think it's going to be start with the box, pour a small bowl, pour a large bowl, and that's the expression, the mathematical model of which we must find the mean and the standard deviation. So press pause, try to find both of these on your own. Pause. And we're back. So for the expected value of Z, you're basically going to take 16.3 minus 1.5 minus 2.5. So that should come out to 12.3 ounces. Basically 16.3 minus 4. And then the standard deviation is going to be the square root of the sum of the variances. So 0.3 squared plus 0.4 squared plus 0.2 squared. And that one we might actually have to take to the calculator. So if I'm going to find the square root of 0.2 squared plus 0.3 squared plus 0.4 squared, I can type this in to get about 0.538. Pull that in right there. So we're going to call that 0.5385 ounces. Any questions on that one? Yeah, question? Yeah, go ahead. Oh, yeah, I see what you're saying. No, that's a good question. Yeah, the answer is I have no idea why it's so cold today. Let's go on to the next question on the next page. We're on problem 39, more cereal. You know how it is. So you finish eating your cereal and there's still milk in the bowl, so you have to pour in more cereal. Let's read it. In exercise 37, we poured a large bowl and a small bowl. Large bowl, I believe, was Y. Small bowl was random variable X of cereal from a box. Suppose the amount of cereal that the manufacturer puts in the box is a random variable with 16.2 ounces. Okay, that's weird because on the previous page, the box of cereal had 16.3 ounces in it. So I guess this is a different box of cereal. This one, we're using 16.2 instead of 16.3. And yeah, so you should be able to figure these out on your own. Find the answers to parts A. Wait, I just want to double check to make sure we're on track with what they're asking. Yeah, so basically this one's pretty similar to what we did before. So we're going to press pause, try parts A and B on your own. Okay, we're back. So there are actually two differences here. One is that it's 16.2 instead of 16.3. Secondly, the standard deviation is different this time. It's only 0.1 for the standard deviation of the number of ounces of cereal in the box. So it's 0.1 squared plus 0.3 squared plus 0.4 squared. That, I believe, comes out to be approximately 0.51 ounces for the standard deviation. So now in part C, if the weight of the remaining cereal can be described by a normal model, what's the probability that the box still contains more than 13 ounces? So we need to get a distribution for Z minus X minus Y. It's a normal distribution, so draw a bell curve. Its mean is 12.2 ounces with a standard deviation of 0.51 ounces. So put the center at 12.2. And okay, so wow, we still have more than 13 ounces left. So the cutoff is 13, more than 13 ounces. So try to find this probability. I'm going to ask you to use the normal model 12.2 comma 0.51. Try this one on your own. Finish it up, I'll press pause. Okay, we're back. My calculator work was 1.57 comma 999 for an answer of 0.058. Here's the work that I did. My x minus mu over sigma came out to be 1.57. And therefore the calculator work of 0.058 gets arrowed in right here. Count of 1, 2, 3, 4. So 0.058 is the probability. Let's go on to the next page. Now for the weightlifting problem, we have the Atlas Bodybuilding Company. ABC sells starter sets of barbells that consist of 1 bar, 2 20-pound weights, and 4 5-pound weights. Now, for variable definitions, we have basically each one of these is a random variable. The bar has a variable amount of weight. It's basically random. Sometimes it's heavier, sometimes lighter than average. So we'll let B represent the weight of the bar, weight of the bar. 2 20-pound, 20 begins with a T. So T for the 20 lb weight. And let's use F for the 5-pound weight. Okay? Bar B, 20-pound weights T, 5-pound weights F. Okay, so that means it's standard deviation. And oh, look, COP, it's all right here. So B, here we can put the word true. This is like the true weight. There's the average weight and the true weight. B is for the bar. And it'd be a good idea to write down the given information. Okay. The bars weigh, so let's write that E of B is 10. SD of B is 0.25. The expected value of the 20-pound weight, or E of T, there's what you would expect. So for 20B20, standard deviations are 0.2 for the 20-pounders. The expected value of a 5-pound weight is 5, with the standard deviation of the 5-pound weight is given as 0.1 pounds. Assume the weights are normally distributed. Okay, now they send them in 2 boxes. The bar goes in 1 box, the 6 weights go in the other. Because what, it's 4 of these 20-pound weights. Yeah. Okay. So let's find out what question they're asking. What's the probability that the total weight in the second box exceeds 60.5 pounds? So the second box doesn't have the bar in it, just the 4 20-pound weights. So the question is, what's going on here? Is it should we use the model expected value of 4 of the 20-pounders plus 2 of the 5-pounders? Or should I use the model expected value of T1 plus T2 plus T3 plus T4 plus F1 plus F2? And you guessed it, this is the model. This is not like a yogurtizing situation where we take a 20-pound weight and magically multiply it by a factor of 4. No, we're taking 4 20-pound weights and 2 5-pound weights. That's much more important for the standard deviation calculation than it is for the mean calculation. But when you put all this together, you will get a mean weight of 60 pounds. Okay, no surprise there. What's the standard deviation? Try to do the standard deviation calculation on your own. I'm pressing pause and we can come back. Okay, so yeah, I found the mistake. There's not 4 20-pound weights. It says there's only 2 20-pound weights. So you probably already caught that. So let me fix that right now. So there's 2 20-pound weights and 4 5-pound weights. And so may as well just get rid of this. So we have to change it anyway. I mean, yeah, the answer is 60 pounds, but the correct model that we should be using here is T1 plus T2 plus F1 plus F2 plus F3 plus F4. Okay, so 20 plus 20, it's 40, 45, 50, 55, 60. Yeah, so it's still 60 pounds. But for the standard deviation calculation, it's going to be 0.2 squared plus 0.2 squared plus 0.1 squared plus 0.1 squared 4 of these. Now, I would write that as 2 times 0.2 squared plus 4 times 0.1 squared. And I think this is where a calculator comes in handy. So on the calculator, we're saying 2 times 0.2 squared plus 4 times 0.1 squared. We're getting 0.3464. So 0.3464, that's an approximation. That's pounds is the standard deviation, 0.3464. Okay, so assuming that the two weights of each piece are independent of one another, the total weight can be modeled by a normal model. Going to use the model N for normal, 60, comma, 0.3464. And remember what the question is. They're saying, what's the probability that the total weight of everything except for the bar is more than 60.5 pounds? Model, mechanics, conclusion. So we've got a normal model. We'll label it. And we want to know what's the probability that we're going to exceed 60.5. So I'm going to press pause, try to find that probability on your own. And we're back. Looks like the answer is 0.0735 and 0.0735. And that came from a z-score of 1.45, and normal CDF gave you the answer, 0.0735 or 0.074. Now, according to the normal model, shipping box, probably that it exceeds 60.5 pounds is that. Now, part B. It costs ABC 40 cents per pound to ship the box containing the weights. And because it's an odd-shaped package, though, the shipping bar costs, it's not coats, it's costs 50 cents a pound plus $6 surcharge. Find the mean, the standard deviation of the company's total cost for shipping a starter set. So the cost is going to be $0.4 times the expected value of the weights plus 0.5 times the expected value of the barbell plus an extra $6. That's a surcharge. So what was this? This was T1, T2, F1, F2, F3, and F4. So the mean would be the expected value of that. The 0.4 comes out front. Yeah, so this is going to be basically filling in the same symbols. T1, T2, F1, F2, F3, F4. And when you multiply all that out, it comes out to $35 is what the expected cost is. Now, I don't like the fact that this is filled in here. So I think it's filled in on your paper. So let's pretend that's not there. And let's get the standard deviation. To get the standard deviation, let's actually show our work. I think you'll learn a lot more if you do the writing. So for the standard deviation, remember we had, so that 0.4 is going to multiply onto the standard deviation. And the 0.5 also multiplies into the standard deviation. So the way that I would set this up is we're going to take 0.4 and the the 0.4 gets multiplied by all of these. So I'm just going to factor out the 0.4. And since we're looking at the variances that add, each factor of 0.4, when it multiplies onto a standard deviation, it'll get squared. So that's why we're factoring out a 0.4 squared. So it's going to be 0.4 squared times all of these variances, which if I recall correctly was 0.2 squared plus 0.2 squared plus 0.1 squared plus 0.1 squared plus 0.1 squared plus 0.1 squared. Okay? And then the 0.5 is going to multiply onto the standard deviation of the bar and then get squared. So it's really going to be 0.5 squared times the variance of the bar. And remember, the bar's standard deviation was 0.25. So it's 0.5 squared times 0.25 squared. That's what has to be typed into the calculator. And if you take the time to type that in, you should get 18.7 cents. Standard deviation of $0.187. Let's check that to make sure it's right. So let's type in the square root of 0.4 squared times the quantity, 0.2 squared, we had 2 of those, and 0.1 squared, we had 4 of those. Okay, so that is the variances for the weights. Now let's add on to that the 0.5 squared times the 0.25 squared. And yeah, that's where we got the 18.6 cents, 18.66 cents, so it's 18.7 cents. So yeah, that's correct. So the shipping cost has a mean of $35 and a standard deviation of $0.187. Next page. Suppose a customer puts a 20-pound weight at one end of the bar and 4 5-pound weights at the other end of the bar. He expects the two, that's a typo. She expects the two to weigh the same. They might differ slightly. What's the probability that the difference is more than a quarter pound? So there's a lot at stake here. You know, lifter's like, whoa, his side's too heavy. It's, all of a sudden you lose control. You don't want that to happen, but it could. So 4 on one side, and what's the difference between them? So a 20-pound weight on one side, and then what's the difference between a 20-pound weight and F1 plus F2 plus F3 plus F4? That's the model we're looking at. But remember, variances add even when we subtract. Now, I have a feeling that that you'll find the hardest part of this problem to be the fact that the difference could be a quarter pound too heavy or a quarter pound too light. Now we expect the difference, the expected value of T minus F1 plus F2 plus F3 plus F4 is equal to 0. I would like you to calculate the standard deviation on your own though, and I'm going to pause while you calculate the standard deviation. All right, we're back. So the plus sign is here even though we're subtracting. So we have 0.2 squared plus 4 of these 0.1 squareds. And I hope when you type that into the calculator, you got 0.2828 pounds. Oh, I forgot the label there, 0 pounds. So the difference can be modeled with a normal model with a mean of 0 and a standard deviation of 0.2828. That's not 0.228, it should be 0.2828. Okay, now, this is gonna be a little bit different of a picture than we've seen in the past. You wanna know what's the probability that we have a difference of positive quarter pound or more, or negative a quarter pound or less. So here's what I recommend we do. Let's find this area right here and multiply it by 2. Because of symmetry, whatever we get for this area, for this tail, is going to be the same as that one. So we can multiply it by 2. So here we go. The z calculation, x minus mu over sigma. Oh, I have to save the document. And I just want to make sure I hadn't pressed pause there. So z equals x minus mu over sigma. When you do that calculation, you're going to get a z-score of 0.844. So z is 0.844. So here's what's new about this problem. Because it could be either more than a quarter pound or less than a quarter pound, we're going to have to take 2 times the normal CDF of this z-score, which is 0.844, comma 999. So the probability is actually pretty high. I'm getting 0.3987. 3987. And I think z-score 0.884. Oh, I typed in 0.844. That's a typo on my part. Yep. It actually comes out to 0.884. So when I make that correction, 0.884, we get a slightly different answer of 0.3767. So we're going to call that as the answer. 0.3767 is the probability there. So that concludes the lesson. Now, the homework is going to be posted. If you just read the message I sent you, you'll find out what the homework is. And also, I'm going to give you a practice quiz. So we'll see you on Friday. Stay warm. Have a good night.